Hi friends, and welcome to our lesson 5A here in our kinetics, thermodynamics, and equilibrium unit. And here we're going to talk about actual calculations of spontaneity to determine whether or not a process is spontaneous or not. We're going to bring in some math. And of course, the letter after the number means that this is very much an honors-only lesson. What you have in this graph are the four possible situations that we talked about in our last presentation in terms of enthalpy and entropy changes during a process and how that relates to whether or not they're spontaneous or not. You can see that one process is always non-spontaneous, one process is always spontaneous, and two processes shown in yellow can be spontaneous or not, depending upon how much free energy is available for them to occur. And that's what we're going to talk about in this presentation. So let's go in. The concept of free energy was developed by Josiah Willard Gibbs, and so as a result it's called Gibbs free energy, and it's symbolized with a G after the man himself. And this is a measurement of the energy that's available in a system to do work. You can think about free energy as like a subset of energy more proper. Free energy is available to do work. All of the energy in a system is not necessarily free energy. If the change in free energy, if the delta G of a particular process is a negative value, then that reaction is a spontaneous reaction. And what Josiah Gibbs figured out was that this relates to the change in enthalpy, the change in entropy, and the temperature. The relationship that describes this is that the change in Gibbs free energy is due to the change in enthalpy, delta H, minus the product of the temperature times the change in entropy, or delta S. This equation is on your honors reference tables, so you have it if you ever need to use it. We're going to talk about how to use it right now. So let's go back to those four situations that we talked about in our last presentation and think about how they work in terms of Gibbs free energy. Let's look at our four situations. So if we have an endothermic process with a negative delta H and that increases entropy, so delta S is positive, that will always result in a negative delta G value. A negative number minus a positive number is always going to be negative, which is why this is always spontaneous. Also remember that since the temperature is in Kelvin, the temperature value will always be positive. If we look at the opposite situation, that is never going to produce a negative delta G. A positive number minus a negative number is always going to be a positive number. It can never not be. So as a result, these kinds of processes, endothermic processes that decrease entropy, will never be spontaneous. Then we have our two weirdo situations. If we have an exothermic process that decreases entropy, in order for delta G to be negative, our T delta S term has to be small enough so that when we end up combining it with our negative delta H value, we do not wind up with a positive number. This is why exothermic processes that decrease entropy are only spontaneous at low temperatures. At higher temperatures, that T delta S term becomes too great and our overall delta G value will become positive. Similarly, endothermic processes that increase entropy are only spontaneous at high temperatures. If delta H is positive, the product of T delta S has to be large enough so that when we subtract it from delta H, we wind up with a negative number. This is why endothermic processes that increase entropy are only spontaneous at high temperatures. So these are the four situations that we need to be familiar with. You're given an honors reference table that has energies of formation for compounds at 1 atmosphere and 298 degrees Kelvin. So standard pressure, but not standard temperature. This is honors reference table B. Honors reference table B tells us about the spontaneity and the changes in enthalpy associated with making these specific compounds at these particular conditions. Anything with a negative delta G will be made spontaneously from its elements, and anything with a positive delta G will be made non-spontaneously. Of course, we can also reverse these values for the decomposition of these substances into their elements at 1 atmosphere and 298 degrees Kelvin. So if something is made spontaneously, it will be decomposed non-spontaneously with the same delta G value, but just with an opposite sign. The same holds true for delta H. If it's endothermic going one way, it has to be equally exothermic going the other way. We can use reference table B in the Gibbs equation to solve a variety of problems related to the spontaneity of different processes. Let's go and look at a couple of examples. This example is from page 18 of your Unit 9 packet. This is what we'd just consider calculating delta G. So calculate delta G and determine if this reaction is spontaneous. Pause the video and try it on your own, and then when you're ready, we'll go through it together. So for this, I'm going to use the Gibbs free energy equation, and I'm just going to plug in my values. we know that delta H is negative 30.0 kilojoules, and we know that delta S is negative 0.010 kilojoules per degree Kelvin. We also know that we're working at a temperature of 298 degrees Kelvin. Substituting in all of my values, I get that delta G is going to be equal to negative 30.0 kilojoules minus the product of 298 times negative 0.010 kilojoules per Kelvin. Working this through, it winds up being negative 30.0 kilojoules minus a negative 2.98. And so we wind up with a free energy of negative 27.02 kilojoules. The negative sign means that this is a spontaneous process. Does that make sense? If you have any questions, write them down before we move on. Let's look at another kind of example from page 19 in our Unit 9 packets. Here we're going to calculate delta S. I'd like you to calculate delta S for the formation of ammonia. You can assume that we're doing it at 298 degrees Kelvin. Hint, hint. Pause the video and try it on your own, and then when you're ready, we'll go through it together. So the first thing we're going to need to do is rearrange the Gibbs free energy equation to get delta S by itself. Add T delta S to both sides, subtract delta G from both sides, and then divide both sides by T. That gives us that delta S is going to be equal to delta H minus delta G divided by T. Now that we know that, we can plug in our values from Honors Reference Table B. We know that we've got a delta H of negative 46 kilojoules. We've got a delta G of negative 16 kilojoules. So it becomes negative 46 kilojoules minus a negative 16 kilojoules over the temperature for reference table B, which is 298 degrees Kelvin. Doing this, we wind up with negative 30 over 298, which winds up being negative 0.10 kilojoules per degree Kelvin as our delta S value. There is a decrease in entropy associated with the production of ammonia at this particular temperature. Does that make sense? If it doesn't, make sure you write down any questions you have, and then we can move on. The last thing that we're interested in when dealing with spontaneity calculations is what's called the equilibrium temperature. Systems in nature that are not always or never spontaneous are the only systems that can really reach chemical equilibrium. This happens when certain temperatures are reached. At these particular temperatures, delta G is 0. When delta G is 0, that's the hallmark of an equilibrium situation. Let's go in and take a look at how we can use this information to figure out the equilibrium temperatures for a particular process. Let's look at an example of calculating the equilibrium temperature. This is not in your packet. Determine the temperature at which the formation of NH3 reaches chemical equilibrium. Pause the video and try it on your own, and then when you're ready, we'll go through it together and see how this works. So first, let's rearrange our Gibbs free energy equation to get this to work. Remember that at the equilibrium temperature, delta G is equal to 0. So 0 is equal to delta H minus T delta S. Add T delta S to both sides, and then divide both sides by delta S. You wind up with T, the equilibrium temperature, equal to delta H divided by delta S. We can then use that equation to plug in our values, negative 46 kilojoules and negative 0.10 kilojoules per mole. The first is, of course, on reference table B, and the second we calculated in our type 2 problem example. And we get an equilibrium temperature of 460 degrees Kelvin. That means that the production and decomposition of ammonia from its elements reaches equilibrium at a temperature of 460 degrees Kelvin, which is a little bit less than 200 degrees Celsius. Does this make sense? If it doesn't, take a moment and write down any questions that you have before we wrap up. Thanks so much for watching our discussion of spontaneity calculations and the Gibbs free energy equation. Make sure you can do the following things here at the end. Make sure you can interpret and explain the concept of free energy. Also make sure that you can use and interpret Honors Reference Table B. Finally, make sure that you can use the Gibbs equation to solve for free energy, changes in entropy, and the equilibrium temperature. If you can do all these things, you're doing great. If not, that's okay too. Take a moment and write down any questions that you have. You can always leave those questions in the comments below the video, or you can always get in touch with me. Thanks again for watching. I really appreciate it. Have a great day.